All right, hey everybody, we are doing clustering today, the second of our unsupervised learning methods. And today we're going to talk about two kinds of clustering. We'll get into it in a little bit. Just again, to quickly recap, because this does get asked in interviews a lot, the difference between supervised and unsupervised learning. So as I mentioned yesterday, and I think will be a little bit more clear today, within supervised learning, the system is basically trying to learn from previous examples that are given. However, in unsupervised learning, you're trying to find patterns directly from the example given. So yesterday when we talked about PCA, it was all about finding linear combinations of features that maximize variance as much as possible in your entire data set. Clustering is kind of the same. So clustering, we're finding patterns directly from, our unlabeled data, which we'll talk about more as we get into it. So if the data set is labeled, it's typically supervised. If the data set is unlabeled, then it is unsupervised. With clustering, we'll actually see that if you have unlabeled data for maybe you just don't have a target, but you do want to predict something, clustering is actually pretty useful for creating labels for your data. And I'll talk more about how that can be done in a little bit. But let's talk about clustering as a whole first before we start breaking it down into specific algorithms. And we're going to hit two main algorithms today. So the whole idea of clustering is dividing your data into groups of clusters, In plain words, the aim is to segregate groups with similar traits and assign them into clusters. So let's just say we have this original unclustered data. You're going to tell your algorithm, okay, I want to take all my data and put it into 3 groups. It's going to create these 3 groups. So you have the blue group, the green group, and the red group. Within clustering, there's actually a bunch of different clustering algorithms. We're going to talk about the 2 main ones, and both of the ones that we're going to talk about fall under hard clustering. Soft clustering, I'll talk about that. We're going to do one example with regards to natural language processing next week, but you'll probably come across other clustering methods if you ever do like outside research, or maybe you come across it in readings on Medium, so on and so forth. But broadly, there are 2 different kinds of clustering. First, there's hard clustering. And for hard clustering, each object or data, each data point belongs to one cluster, fully one cluster. So for example, in clustering New York City locations, each location belongs to either one borough or the other. So for the algorithms that we're going to talk about today, each data point is strictly going to be assigned to one cluster. Now in soft clustering, a data point can belong to more than one cluster with a probability or likelihood value. So for example, you could identify some locations as border points belonging to 2 or more boroughs. Basically, it becomes like probabilistic clustering, where you can get a probability of, all right, well, this data point, maybe there's like a 60% chances in cluster 1, 40% chances in cluster 2. Both the methods that we're going to talk about today are hard clustering methods, but interestingly, one of them you can actually pull out probabilities of belonging to a cluster, but that's not how the algorithm is working. So within our hard clustering methods, and actually within soft clustering, you can actually classify it into either one of these 2 clustering methods. So first you have centroid-based clustering, as well as connectivity-based clustering. So the 2 algorithms that we're going to talk about today, the first one is a centroid-based clustering method. That's Kmeans clustering. That's what we're going to talk about first. And then connectivity-based clustering is the second kind. We're going to talk about hierarchical agglomerative clustering, or AJC. That falls under connectivity-based clustering, and it's all about how the clusters are being formed by the algorithm. So first, in centroid-based clustering, clusters are represented by a central vector or a centroid. So basically, somewhere in your feature space, the cluster is identified by its center. The centroid might not necessarily be a member of the data set, because the centroid is pretty much the average of all the data points in a cluster. We'll see how the algorithm works in a little bit as well. And this is an iterative clustering algorithm in which the notion of similarity is derived by how close a data point is to the centroid of the cluster. I actually have a few GIFs and animations to see how the clustering is actually happening. And K-means is what we're going to be talking about. The second algorithm that we'll be talking about, connectivity-based clustering. The main idea of this is that data points that are closer in the data space are more similar than data points that are far away. So the clusters are formed by connecting the data points according to their distance. At different distances, different clusters will form and can be represented using a dendrogram, something that looks like a tree diagram. We're actually going to see some examples of this as well. And this gives away why they are commonly called hierarchical clustering. So these methods do not produce a unique partitioning of the data set, rather a hierarchy from which the user needs to choose appropriate clusters. We're going to talk about that more later. I know all of this probably sounds like gibberish right now. By choosing the level where they want to cluster. So they're also not very robust towards outliers, which might show up as additional clusters or cause other clusters to merge. Okay, so we're going to work through these clustering examples or these clustering algorithms with scikit-learn. So everything is already run in this notebook because AJC, the second clustering method, takes a very, very long time to run. So I don't want to run it during the study group, but everything's run. You can run on your own. I think it roughly should take about not more than 10 minutes for your notebook to run. So everything that we're importing right now, we're just going to start with Kmeans. I'm going to import AJC later. And we're going to use this very, very simple data set. Okay, so to start, K-means clustering. How does the algorithm work? So first, it chooses based on the number of clusters that you want. And by the way, for either of these clustering algorithms, you have to tell your algorithm how many groups of data you want to end up with. So you tell it how many clusters you want. It's going to pick some centroids and then start assigning points to the centroids. So actually, let me show you these to start. But I think this will make it a little easier to understand. This is already run, so let's start from the start. So this is kind of the algorithm at work. What happens here is this algorithm decided, okay, I want 4 clusters. I'm going to start by picking the leftmost 4 points and then assigning points to a cluster based on which is the closest centroid. And then the centroids are going to shift after every iteration. And then you're going to reassign these clusters. So let me just refresh this again. So you can see here, what's happening here is for every single data point, it's going to see which is the closest centroid to it. So when all of these dots are done connecting, you'll see that the centroid is going to shift. And the centroid doesn't have to shift to be another data point. It's just going to be the middle of the data points. And then it's just going to reorganize itself over and over again until nothing else has to change. Any questions about this process? I'm going to refresh it one more time. It's actually pretty neat how this works, I think.
So does the centroid start on data points and then it kind of moves off and does its own thing?
That's a good question. So where the centroids start, it's fairly arbitrary, actually. You can tell it where you want the centroids to start. Actually, in this notebook, I have a couple other examples. I'm going to keep this up here and with another example. And this is, I have 4 different GIFs here, which you can, of course, play around with. I have 4 different ones that start their centroids at different parts of the data set. It doesn't necessarily have to be a data point. It can really just be an arbitrary part of your feature space. So maybe you want to start it 4 right in the middle here. You can do that too. But I do want to show that based on where you start your centroids, you can end up with different clustering results. So right here, we're starting from the right-hand side. And when this is being done, hopefully this doesn't take too long. When this is being done, you'll actually see that the end results are going to be different because we started on the right instead of the left. And I'll show you all the documentation for K-means in a little bit. They actually have their own way of deciding how to start, but you can also feed in your starting centroids. So you can see here, I think the resulting clusters actually end up with 3 groups here and then 1 group by itself, just 1 data point in this 1 group, which I think is different. It's different from this version that started on the left. So it is quite sensitive to where you decide to start your centroids. Also dependent on your data set. If your data set is fairly uniform, if you have a lot of outliers and you accidentally choose your outlier to start as a centroid, this might happen as well. And you end up with uneven clusters. But yeah, point of this is to show that wherever you start your centroids could potentially change the outcome of your clustering. Let me pull up the documentation. So here, you can tell it how to initialize the centroids. So you can give it an array of where you want it to start. but for the most part, you just let it decide how it goes. So the default is Kmeans++, and honestly, I haven't looked into it either, but Scikit-learn just has an algorithm for figuring out where the best starting centroids will be, and they'll just use that. So far, I
Awesome,
haven't
thank
had any issue with that. Yeah, you're welcome, Dimitri. But yes, cool. Other things that you can check out with K-means is init. If it really matters to you, like how your clustering is being done, you can actually have it run 10 different K-mean algorithm, 10 different K-means with 10 different initial clusters, and it'll just choose the best one based on inertia. And I think we'll talk about inertia in a little bit as well, but inertia is just one way that you can use to evaluate your clusters. But yeah, now that you've seen like visually how K-means clustering works, I think the math would make a little bit more sense. So we're really just using distance metrics. So kind of, I mean, it's K-means, sounds very similar to K nearest neighbors. It actually is using nearest neighbors, but not in the same way as classification model is using it. But you're going to take distance measurements between your centroids and your data points. And then of course, you're going to associate your data point to the nearest centroid. And in calculating distance, there are also a few different ways where you can do it. I think the default might be, let's see, distance, pre-compute distances. Let's see here. Oh, okay. I forget what the distance metric is. I think by default, it might be Manhattan distance because it's all relative to each other. So yeah, Manhattan distance. It's just the absolute value between the feature, the absolute value between the centroid and the data point based on its features. So Manhattan distance, we had talked about that when we talked about K nearest neighbors, and you're just taking the sum of those differences. And then whichever one has the smallest value, you'll associate it with that cluster. And you're just going to keep updating that until basically the algorithm no longer updates the centroids when there is no change in the current cluster formation. So the math, fairly simple. It's just a lot of calculation going on. So we went through this already. So how do we use it? So this is our data. It's very, very simple. It's just 2 dimensions, and we're going to do some visualization on this data, which is why 2 dimensions is easier. I'm going to instantiate my K-means with 4 clusters and fit my data. So it actually uses very, very similar syntax. Oh, shouldn't have run it. You saw that already, but basically we're fitting our data there. This is what our data set looks like, and these are our cluster centers. Actually, you know what? Let me just run it, just so we can see this at work. Right, so we have our data. This is what our data looks like. I have fit my data to my K-means, and again, you just tell it how many clusters you want. And then this is my data.describe because these are our cluster centers. So these are our cluster centers. This is just the mean values of our, the .describe of our data set so that we can associate where these values are. If you want to assign clusters, you can actually assign your test set clusters based on your train set clusters. You can do that using .predict. I'm not doing a train test split here, but just to show that you can use .predict within your K-means. And you can also concatenate your cluster numbers to your data. So over here, if I rerun this, hopefully later it won't take too long to run. When I rerun this, you can see that each of my data points has been associated with a specific cluster. And you can see here, I have my 4 clusters here, cluster 2, 0, 1, and 3. Cluster 2 has 952 data points. That's the most. And cluster 3 is the smallest with 521 data points. And just like that, we've grouped our data into 4 different groups. Now we can do a little bit of inspection of how you want to define your clusters. One thing to note is that these clusters are being generated mathematically, purely mathematically. It's not really taking any context into consideration. So if we take a look at this 2-dimensional data set over here, you can sort of see that your cluster centers for your x-axis, let's just look at, or your V1 axis, are at 9, 47, 69, and 31. If you look at the range of your values over here, your mean is about 4, your min is -22, max of 104. You can sort of start to visualize where these clusters are. Of course, if this had context, if it wasn't just V1 and V2, you can start to think about, okay, maybe these are like heights and weights, for example. These are heights and weights. You can look at these cluster centers and be, okay, well, maybe like the people in this cluster are these people, the people in this cluster are these people. And then you have to manually label your clusters. So yeah, based on this, you could see that maybe clusters 1 and 3 are fairly similar to each other based on like the y-axis being kind of the same and the x-axis is relatively equal as well. Cool. From that, we can visualize our clusters. I should definitely added a legend here to see which one it is, but now you can see that through this K-means, you have taken our data and we have grouped our data into 4 distinct groups. Questions about implementation? I do want to really hammer home the fact that these clusters are generated mathematically. So if any clusters don't make sense, like for example, you might think, okay, well, I asked for 4 clusters, but now looking at this data set and this visualization, it looks like the light blue and the dark blue should maybe be grouped together. You definitely can make that call. You can definitely say, well, based on what I'm seeing in visualizations, maybe I'm doing some like EDA based on my clusters. I'm going to say and make an executive decision to combine the light blue and the dark blue clusters. You can 100% make that call. It really depends on the context of what you're doing.
So to do that, we would change it to 3 and rerun it?
Yeah, actually, that's one way to do it. You can change it to 3 and rerun it. Your results might change quite drastically. Well, let's actually see what happens when you do 3. Because sometimes if you change it to 3, I mean, this data, it's kind of obviously already generated for clustering purposes. But if it's less clear cut, maybe if you did it to 3, your results might not be like 1, 2, 3 like that. So you can make the executive decision to maybe make more clusters and then decide how to combine them based on some inspection. So actually, let's really quickly see what happens when we do 3 clusters. At 3 clusters, we have, sweet, as expected, because this data set looks like this, we have 1, 2, 3 like that. But there is a chance that if you, maybe I decided this data set was not so nice and I decided to do 3, maybe it would have turned out slightly different. Like maybe it would be like, I don't know, like part of this group and part of another group. But for this data set, pretty obvious. But yeah.
Thank you.
You're welcome. Okay, so next I want to talk about finding best K. When you have to find your best K and when you decide what the best K is, truly depends on your context, right? Sometimes you're given a contextual problem where it's like someone goes up to you and you're a data scientist and they're like, okay, I want to group all of my users into 4 groups. Now, even if 4 groups doesn't really make sense based on what your data looks like in this case, it looks like it should obviously be 3, but maybe, I don't know, your manager wants you to make 4 groups. You have no choice but to make 4 groups. Of course, I mean, yeah, depending on context. But so sometimes you are restricted or constrained by how many groups you need to have. Other times, not really, right? So let's say you have a market segmentation exercise where you want to look at people's transactions and just group your users. And you're not being told how many groups they want to have. And if you're given a problem like that, you have the flexibility to choose different values of K, of how many clusters you want. And there are several metrics that you can use to do that. So first, there is the within cluster sum of square method. So the basic idea between partitioning methods like Kmeans clustering is to define the clusters such that intra-cluster variation is minimized. And so what is intra-cluster variation? Intra-cluster variation is basically the distance, the average distance between a cluster's centroid and every single one of its data points. So you want to minimize this distance as much as possible, but every data point still has to belong to a single cluster. So this total distance plus this total distance plus this total distance will be automatically minimized in K-means clustering. However, we do want to see that, okay, maybe if I were to make more clusters or fewer clusters, the overall distance will get smaller, and we'll see this elbow graph in a little bit. But that's basically the within cluster sum of squares. So we're minimizing within clusters sum of squares. So the total WSS basically measures the compactness of your clustering, and you want it to be, again, as small as possible. So the elbow method looks at the total WSS as a function of the number of clusters. So one should choose a number of clusters so that adding another cluster doesn't improve the total WSS by much. Now, what does this look like? Okay, so most nice clustering data sets will have a curve that looks like this when you plot your WSS. Now, just naturally, every time you add a cluster, WSS is bound to go down. It will always go down, right? Because if your cluster covers a smaller distance or a smaller amount of space, your overall distance is going to be smaller. So this line will pretty much always be decreasing, but there's typically an elbow to this graph. And in this case, you can see that there's a very obvious elbow at k equal to 3. Because if we are going from 3 to 4 to 5 to 6, yes, the WSS is going down, but not by much, right? Because as you can imagine, I'm just going to guess here, the clusters, if you were to further divide your clusters, it will probably look like, I mean, as we know, when we did the 4, it probably looks something like this and like this. And if we were to further divide maybe these two, maybe you divide these two, the distance is not going to go down by as much as maybe if we started with 2, they had like one big cluster here and one big cluster here, the distance was much, much larger relative. Hopefully this isn't too messy now, but hopefully that makes sense. So if you have the flexibility to determine the number of clusters in your data set, one way to do it is to check for your WSS and find the elbow. All right, so here, yeah, the marginal decrease is subsequently reduced. So as you can see, from 2 to 3, huge decrease, but from 3 to 4, 4 to 5, and so on and so forth, the decrease is not as much as it was from 2 to 3. So based on this graph, the best K, I mean, also obvious from our visualization of our data, best K is 3. Of course, usually is not this obvious. In every like real life clustering problem I've ever had to work on, it is never this nice. And you usually have to choose between 2 or maybe 3 values of K. But you would look for an obvious bend in your line graph. Okay. So the other metric that you can use is silhouette coefficient. So average silhouette basically measures the quality of your clusters, how well each object lies within its cluster by estimating the average distance within each cluster. So basically, it's looking at the relative distance for every single data point. How good is this data point in its assigned cluster versus if it were in a different cluster? So let's say for this data point over here, let me just like mark it real quick. For this data point over here, how good is it in this cluster versus being assigned to this cluster and this cluster? So that's what silhouette coefficient conceptually looks at. So it's a measure of how similar one data point is to its own cluster compared to the other clusters. So silhouette ranges from -1 to 1, where high value indicates that it is well matched to its own cluster and poorly matched to neighboring clusters, which is ideal. If most objects have a high value, then the clustering configuration is appropriate. But if many points have a low or negative value, then clustering configuration might have the wrong number of clusters. So the silhouette can be calculated with various systems metrics. So this is what the silhouette plot looks like. I'm not going to run this. Here you can see that over K, this red line is our average silhouette score, but you just want to maximize your silhouette score, your average silhouette score. And as you can see here, your average silhouette score is the best at K equals to 3 as well. So using these two metrics, you can use these to decide on what the best number of clusters to pick. But again, if you are constrained by the number of clusters, there's really no point to looking into these metrics. So it's really dependent on whether you have the choice of how many clusters you want to look at. Cool. Any questions at this point? Okay, awesome. So what are some pros and cons of K-means? This is a really neat article. I'm not going to go through it right now, but it talks about the very. Here, let me just pull it up to get the gist of it. To talk about the basically why K-means isn't always a good thing, because it is a very distance-based algorithm, I think. Also, oh yeah, basically, this is what that article is talking about. So it's 3 scenarios where it is not good to use K-means. All right, let's move on to talk about AJC, hierarchical agglomerative clustering. I'm going to pull up the documentation right now here as well. Okay, so K-means is kind of a very top-down approach to clustering. If you think about it from a top-down approach, it is first deciding on where the centers are and then slowly shifting the cluster centers. AJC does it kind of the opposite way. It actually starts with a bunch of clusters and then merges clusters together. So it basically sets out to group most similar 2 observations together from a bottom-up level. Initially, every observation starts as its own cluster, and then the most similar pairs of observations form a cluster together, and the next most similar groups fuse together, and we just continue this pattern upwards until you have one giant cluster. What you end up with when you do clustering like this is a tree-like diagram called a dendrogram, and we'll actually see an example of that. I'm not going to run those cells, and that basically allows us to view the clusters attained for each possible number of clusters from 1 to n being the number of data points that you have. And so you use your discretion to decide where to cut off the dendrogram, determining the number of clusters. For AJC, you can also use either the elbow method or the silhouette coefficient to evaluate your clusters too. Cool. So versus K-means, K-means assigns individual observations to a pre-specified number of clusters according to the distance between centroid and observation. One disadvantage of K-means is that we have to specify these number of clusters, but for AJC, you technically do not have to. We'll see that in the documentation, they still ask for how many clusters, but what it's doing is you actually have the full tree. You can do compute full tree here, but I'll show you why that is the case. We'll go into the pros and cons in a little bit.
Sorry, real quick before we move on. So for the silhouette check, right? I noticed that it starts to creep back up. Is it is it possible that once you increase it to a certain level, it might get somewhere near the original 3?
Honestly, maybe. So if you imagine that, like, perhaps if you zoom out of here, or I guess zoom into here, there is a potential that within these 3 blobs, maybe there's like millions of data points in here, and you can actually subgroup your clusters. So yes, you can actually end up, because it is a relative score and it is a ratio, there is a potential for it to creep back up. And there is potential that, like, for maybe 2 clusters is great, but ideally you don't want to have 2 clusters in whatever your problem is, but maybe later at like 20 clusters, it's also
Would we be able to use the silhouette check to see that just by extending the graph?
Yes, yeah, absolutely. So if you were to do, let's see, if we look at range 2 through 20, hopefully this doesn't take too long. So we do 2 through 20, let's do this. All right, it shouldn't take too long. All right, but there we go. Yeah, as you can see for this case, because that data set looks like that, it doesn't end up going up, but there would be scenarios for sure. I can definitely see that if you have like a bunch of subgroups and if you have a lot more features as well, that's definitely possible.
So thank you. I was just thinking about that and I want to move on.
All good, all good. Okay, so back to AJC. Okay, so a visualization to show how AJC works. You can see these are, I guess, 9 steps in an AJC process. So first you start out with every data point being its own individual cluster. And then what you're going to do is just look for the 2 closest data points and combine them to form their own cluster. So here you can see that the closest 2 data points are these 2. So now you have one less overall cluster because these 2 are combined. You're going to keep doing that. And then now whenever you have groups, the center of each group will be used to compute the distances. So after a certain point, so at this point, we just have 4 pairs and then 4 separate data points here at step 4. From step 4 to 5, it notices that the next closest distance is actually this data point down here to combine with this one. So this then combines with this to make its own bigger cluster. And so that process keeps continuing. Eventually, you're going to end up with one gigantic cluster at the very top. Okay, so before I go into more about that, some pros and cons. The advantages is it's quite intuitive, right? It's all about similarity of your data points rather than similarity to some centroid. It's also more informative usually because it takes individual relationships between data points into consideration. Also, it allows us to look at the dendrogram. I'm going to show you all the dendrogram in a little bit to help decide the best number of clusters. However, the disadvantages, it is very, very sensitive to outliers. And you also cannot undo the previous merge. It's kind of a greedy bottom up algorithm. So let's just say that you maybe think that, okay, this shouldn't have been combined, but you cannot undo this combination anymore. I'm going to talk about this later, but I do want to show you all a dendrogram. This is an example of a dendrogram where at the bottom, actually I have one that is cut off. Okay, yeah. So this is a dendrogram where the very, very bottom is all of the data points. This is not a very clear diagram. Usually when you have a dendrogram, you don't plot the whole entire thing. But for this dendrogram, you can sort of see that how these clusters are being formed. Every time you have like a horizontal line across, it is clusters merging together. So let's just say you wanted to have 2 clusters. Your clusters would be here as well as here. And if you want to have 3 clusters, you have to look for wherever there is 3, which I actually think it might be like combine all the way at the very edge over here. But this is an example of a dendrogram. And I think in your labs, you have a better dendrogram than this that is not so smushed together. Yeah, you can also trim and truncate. Here is an example where you have 4 clusters, where this one has 2,997 data points in one cluster, and then one of each here as your outliers. Okay, but that's a dendrogram. In AJC, there is a little bit of hyperparameter tuning that you might want to do, because one thing that you can tune is the linkages. So with AJC, you can see that linkages is one of the hyperparameters, and it's basically how you determine how you calculate distances between combinations of smaller clusters. Typically, it's not very sensitive to different linkages, but just in case you have a lot of data points that are very close to each other, this might make a difference for those edge cases. So first, there is a simple linkage where your distance between clusters is based on the points that are closest to each other. So the linkage between this cluster and this cluster is basically the distance between its closest points, their closest points to each other. So it's literally just the distance between this data point and this data point. That's the single linkage distance. If you're doing complete linkage, you are looking for the furthest points from each other to compute the distance. So this way you can see that it could be more sensitive to different clusters. You want the linkage distance to be the largest value. So between this one and this one. And then finally, average linkage, where you actually take the distance between all of the data points in one cluster and all of the data points in the other cluster and take the average distance. So that's how those are the 3 different methods in which you can compute the distances between clusters with already more than one data point. And again, I will say like clustering results probably will not change by much. The only thing that would change would be, again, those edge cases. All right, so here, this is code for plotting a dendrogram. Honestly, not very important, especially if you have a very, very large data set, but in case you want it to visualize, this is something that you could do. Alternatively, you can also PCA or use TSNE, what we talked about yesterday, to lower the dimensionality of your data set and then plot. But yeah, these are dendrograms. If you had like a clustering problem and you wanted to decide how many clusters to do, one thing that you can do is look at these linkages. But for bigger data sets, again, doesn't really make too much sense. Okay, so let's take a look at these clustering results. I'm using Kmeans over here to compare, but I'm also putting AJC here. And I'm not going to rerun these. But basically what I'm doing is instantiating AJC, doing a fit predict there. So we have the clusters over here. And we're just going to concatenate the results together so that we can.
And that N clusters in there is how many it starts with?
The AJC?
Yes.
Oh, okay. Yeah, so for AJC, even though it's doing that bottom up cluster, for the purpose of scikit-learn implementation, you got to tell it how many clusters to do. If you did the option of, where is it, of compute the full tree, if you want to do that, it'll actually compute the entire dendrogram, but for the most part, it is still more memory efficient to just stop at however many clusters you want. So that's the reason why you still
did the
gotta
whole
give
tree, it would just give you like the recommendation of how many clusters it thinks is the best.
So you have to, even if you do compute full tree, you still have to give it the number of clusters. But if you wanted to look at the rest of the tree, you can still extract that from, I think you can extract it from either children or, yeah, there's one place that you can extract that information. I forget where right now. Probably you can find that over here.
That would really be the only reason to do that, is to be able to extract that information, right? It's not going to affect the modeling.
Yes. It's not going to affect the modeling at all. If you change the number of clusters, the bottom parts of your tree actually don't change it. That's something I'm going to show you all in a little bit as well. Because if you the thing is with Kmeans, if you rerun Kmeans over and over again, you might get different clusters based on where you initialize your cluster centers. But for AJC, no matter how many times you rerun, you're always going to get the same clusters because it is doing it based on the similarity between your data points.
I see. Thank you.
You're welcome. Okay, so to just quickly compare our results, this is the same data set run through 4 clusters for both of our algorithms. You can see that Kmeans ended up like this, AJC ended up like this. So you get slightly different results. And I think for AJC, we're using all of the defaults, I think, and the default for AJC, I forget, but it is word linkage, which basically minimizes the variance of clusters being merged, which is one that we didn't talk about, but basically it looks for, I think it also optimizes for WSS at the same time. So yeah, basically you just get different results there. Cool. Now, what I was talking about earlier with Dimitri's question, how every time you rerun AJC, the tree never changes, it's just where you truncate the tree that changes, right? So if we take a look at AJC, and I've actually run it a couple times here. Let me open this up. If I do 5 to 6 to 7 to 8 clusters, something interesting that you will see is that the clusters are just being subdivided, or we're looking at it backwards. We actually start from 8, or we start from, I guess in this case, 3,000, and then you're just merging together. So that's why you'll see that when we go from 8 to 7, all we're doing is we're merging this light blue one and this gray one to make this larger cluster. The rest of the clusters are all the same because of this bottom up approach. And when we go from 7 to 6, 7 to 6 looks like we're combining the pink and the blue one up here. And then from 6 to 5, we're going to combine these. From 5 to 4, we combine these. So that's why, well, the tree and I guess the way the bottom up structure is what makes it such that you're just grouping your former smaller clusters together as you get fewer and fewer clusters. And in the end, if you go down to like 2, or if you go down to 3, these are probably going to combine. If you go down to 2, it will combine as well. If you go to 1, it'll just be one big cluster. But the points that are grouped together will always be grouped together. So that's AJC with different cluster values, which is actually really neat. The downside is AJC always has to compute the entire tree every time you run it in scikit-learn. So that's one downside, but you get these more consistent results, I guess. Cool. So again, as I was mentioning before, you can also do your silhouette score and your elbow method for for this method of clustering as well. So for this, I mean, this is kind of expected because, well, it's kind of expected because of how the data set looks, but we have the best silhouette score at 3. The silhouette score should actually be slightly different as well. I should have plotted them both together, but you can see that this was just under 0.7. I wonder if the other one is also, just under 0.7, I guess, but you can see that they should look slightly different because the clusters are different. So idea is essentially something that you could do. You can also do some sort of grid search for clustering if you wanted to. All right, neat. In summary, 2 kinds of clustering. I like to think of them as like top down versus bottom up. Kmeans does have an element of randomness while AJC does not. And in context, you still have a lot of leeway to make your own judgment calls and decision on how to deal with these mathematically generated clusters. So let's say you were clustering, I don't know, football players. If you're clustering football players and you end up with like 5 clusters, you would still have to look into each cluster, and based on the characteristics of the cluster, you get to give it the label itself. Like with these 4 clusters over here, I would have to go in to see, all right, this pink cluster has like averages of about like 10 and 10. You would have to use your context to decide how to label these clusters in the context of your data set. They're not going to name the cluster for you. And also, again, you do have the flexibility to adjust these clusters, maybe even if they go against what your WSS elbow curve or what your silhouette score is telling you. You do have the ability to make the judgment call because context does, I do think in some scenarios, does take precedence over what math is telling you. Like, for example, I've seen projects where students are, again, grouping like sports players. I think that's one of the very common ones that people do. If you're grouping a bunch of sports players and your best number of clusters they're telling you is 2, you got to ask yourself, is it useful to only have 2 clusters, or should I just, even though 2 is giving me the best score, use something else? So that's really up to you to think in context and make that decision on your own. But yeah, that is clustering. In your projects, how you could use clustering, I do think that clustering can be a very interesting EDA tool if you just take a look and see how your data is distributed. Using clustering does help you separate out subgroups of your data that you can look into further. Clustering can also help you generate labels. So let's say you have a bunch of unlabeled data and you want to do some sort of supervised learning. You could use something like Kmeans to generate, let's say, 4 clusters, and then build predictive models to predict these clustering results if you needed to do something like that. So that's something that I've seen as well. So you can actually use clusters as features. That's another thing that you can do too, which is really neat. But yeah, that's clustering. That kind of concludes our unsupervised learning component of this phase. We will talk about, I think, one other method of soft clustering in NLP next week in natural language processing, because that's a very specific to NLP one, which will be very cool to see. But other than that, these unsupervised learning methods are optional to use in this upcoming project. You may or may not want to use them. You may or may not also want to use them in your capstone projects. It's really only if it asks for it or if you feel like it's necessary, but these are definitely good to know things. But yeah, at this point, does anyone have any questions? Neat, cool. All right, well, if there's anything, feel free to let me know. Still, a few of you haven't scheduled your project review, so please do that. And then also, I feel like I always have to remind you all, think about your blog, start thinking about your blog. It says best to get it done maybe in the next couple of weeks as we ramp up to the next project. Cool. All right, if there's nothing else, Slack me if y'all need anything, and I will talk to you all tomorrow, where we will talk about big data. All right, bye everybody.